Welcome everyone. I'd like to begin by thanking you for joining today's webinar and for your interest in learning more about dry hydrogen peroxide within commercial poultry hatcheries. Dr. Brian Jordan will share information with you on his recent study conducted through the University of Georgia, where they compared the efficacy of dry hydrogen peroxide in a commercial hatchery to formaldehyde. He'll discuss the role of DHP and how it can add value to your standard cleaning and disinfection protocols. Dr. Jordan graduated from the University of Georgia with a BSA in 2005 and a Ph.D. in poultry science in 2012. He's since studied avian disease, been an assistant professor with split appointment in departments of poultry science and population health, and was promoted to associate professor in 2022. In 2022, Dr. Jordan became the interim director of the PDRC. His research is very much applied, focusing on bronchitis, virus, vaccines, vaccine technology, vaccine application, and evaluating the efficacy of vaccine programs. We hope you find today's information valuable and actionable. And now I'd like to hand it over to Dr. Brian Jordan to get started.
All right. Hi, everybody. Thank you for joining us today for this webinar. And as has been mentioned, I'm going to discuss several research projects that we have done evaluating DHP and its role in a hatchery and what it can bring to a hatchery sanitation program. And we set about doing this research because if you think about the way that our poultry industry is vertically integrated, we have all of the eggs being laid on these breeder farms, and these breeder farms are all within one complex, but are all independently owned and operated, are geographically distantly located sometimes. And, all of these eggs then get collected and brought together into the hatchery. And so the hatchery becomes a focal point where anything from any one of these individual breeder farms, whether that be microbes, whether it be viruses or other pathogens, could be any number of things, they're all going to get brought from these different breeder farm locations into the hatchery, where all of these eggs are going to commingle together. They're going to be placed together inside incubators. They're going to be placed into hatchers together. These chicks hatch, and then these chicks are then spread back out across different broiler farms that are, again, individually owned and operated and are geographically separated. And so when looking at this system of vertical integration, it is a very effective system for our production environment in terms of efficiency and cost, but it does make the hatchery a very centralized location for trying to combat a lot of the everyday problems that we may face within our production system, particularly microbes, bacteria, viruses, fungus, things of that nature. Now, we know that the health of newly hatched chicks can be severely impacted if they hatch within a contaminated environment, right? A couple of the most common diseases that we see that are directly related to hatchery cleanliness are things like brooder pneumonia, which is an aspergillus fungus infection. You can see a mold spore clearly growing in that egg in the picture on the right. You can see actual fungal lesions. They're called pearl-like lesions in the lungs of newly hatched chicks on that picture in the left. And while you may think that this isn't something that occurs commonly, you'd be very surprised how frequent those fungal infections actually are. And then another thing, omphalitis, yolk sac infection. So when chicks hatch, they have that retained yolk. They feed off that yolk for several days after hatch. That navel, and then what feeds into that yolk sac is the direct connection between that developing embryo and the outside environment through the egg. And a lot of times that yolk sac can get infected, and then that can lead to a further bacteremia, or it could lead to just increased 3- and 7-day mortality itself, right? So if we don't get these chicks off to a good start, we are setting them back in their potential for the entirety of their production life. Now, because of this, because we know that the hatchery is this location where we have to try to control these microbes as much as we can, every commercial hatchery has a cleaning and disinfecting procedure and protocol. And all of these start with removing organic matter. It doesn't matter which sanitizing agent, which soap, which viral, antiviral component you use. If you don't remove the organic material, you don't have access to those pathogens to adequately targeting. So you have to have some little bit of elbow grease here. So you apply or remove the organic material, you apply a soap, you do some scrubbing, you do some rinsing, you have to agitate these things, you have to clean up the environment. An example of a typical soap that might be used would be something like this biogel, right? It's a very common chemical. It has that very high pH. It's going to help break down a lot of these bacteria and a lot of these microbes. Then a lot of times we'll come back with a sanitizing foam, something like a Viracid. And that sanitizing foam is going to help increase your contact time. It's going to help increase your surface area with that foaming agent that's in there, right? And this is going to really help sanitize the surface of your hatchery after you've done that initial soap, scrub, rinse with your standard cleaning agent, right? But even then, this happens every day. We know that that is not enough. We have to then take an additional step to help control microbes. And that's typically done inside the hatchers themselves. Most commercial hatcheries will employ a formaldehyde fog in the hatchers, and we'll talk a little bit more about that later, or something like a hydrogen peroxide fog. Now, both of these have advantages and disadvantages. We actually moved away from using things like formaldehyde in hatchers over the last, say, 30 years in the poultry industry as our use of antimicrobials in feed increased. But in the last 10 years, as there's been a big push for antibiotic-free poultry production, we've removed those in-feed antimicrobials. We realized that we don't have as good a handle on controlling these microbes as we thought we did, and we see a lot of formaldehyde being used again in these poultry hatchers. So you look at this list of things that happen every single day in a hatchery: organic material removal, using your soaps and scrubs, applying a sanitizing foam, applying these chemicals inside the hatchery. You may think, we've got this thing covered. There's no way we could still have issues. Yet we still do. We still have issues related to hatchery cleanliness and sanitation that influence our production and influence our 3 and 7 day mortality. Why is that? Well, the reason is because the very thing that we are doing in the hatchery, bringing in eggs to hatch chicks to send back out to farms, are also bringing in a fresh round of microbes every single day. You see pictures like the ones I've shown here where eggs are covered in fecal material. They're, laid in the litter instead of in the nest box. And we would hope that eggs like this don't get set. But in a production environment where we are trying to fill houses and there's a shortage of chicken being produced, and we call it being short on eggs, we need to set every egg we can to try to get every chick we can to the broiler farm to raise for meat production. A lot of times eggs like this, even though in a perfect world they shouldn't go into incubators, they still do, right? These eggs here are carrying who knows how many millions of microbes. We've done studies in the past, and other researchers have as well. If you look at perfectly clean eggs, nice white or brown eggs with no fecal material, no litter, nothing, no blood streaks, nothing on the egg, looks like a perfectly clean egg. Even those eggs carry up to 10,000 bacteria on the surface of the shell just from the process of being laid, right? So even if we're bringing in our clean eggs, we're still bringing bacteria into the hatchery. Then what happens? As those eggs incubate, those eggshells are porous. Those bacteria move into the egg, into those internal membranes, and that egg yolk that's inside of an egg is a perfect substrate for bacterial growth. And so those bacteria begin to grow. As those bacteria grow and replicate, they produce gas as a byproduct of breaking down metabolism. As that gas begins to fill inside the egg, either that contaminated yolk and bacteria material starts coming back out of the pores, or you get those eggs that we call exploders. And when those eggs explode, they contaminate and coat every other egg around them. They contaminate all the eggs below them in the rack as the material just oozes down through the pores in the rack. And now, as I said earlier, you've contaminated eggs from other breeder farms that are then going to hatch and go out to these new broiler farms, right? So the eggs themselves that we bring in are an issue. So what else can we do to try to help mitigate those microbes, particularly focusing on the eggs themselves, since we've identified the eggs as a place that is a critical control point for these microbes? And there are a lot of things that have been tried, using UV light sanitation, using machines that produce ozone, actually misting hydrogen peroxide throughout the hatchery spaces, not just in the hatcher. using a formalin or formaldehyde wash. This is a very typical practice in Europe and some other parts of the world. We do not wash or clean hatching eggs here in the US. So using that formaldehyde prior to set is not a practice we do here, which is why we ultimately end up using a formaldehyde fog in the hatcheries themselves. And then you've got combinations of these things where you apply ozone and UV light together, sometimes in a separate machine, sometimes internally within the hatcher. And again, all of these things have shown to be effective in some way, but a lot of these components also require manpower. They require full-time employees. You may have to dedicate 2 people to utilizing some of these technologies. And most of these give you a single point clean where once they go through this procedure, you definitely have reduced microbes, but then those eggs are just free. Anything that's inside the shell, anything that, those exploders, they're not going to be affected. So there's always the possible risk of recontamination. So that leads us into this dry hydrogen peroxide technology from Synexis. And we have done research with this for over 6 years now, looking at different experiments. And so we're going to talk a little bit about some of the experiments we've done today. But the way that the technology works is ambient humidity and oxygen. So the natural humidity and the natural oxygen that are present in the air are drawn through this membrane called a sail. And that is a photocatalytic sail. And so that light that you see there in this diagram activates the catalyst on this membrane, and it catalyzes a reaction to actually break the water molecule and the oxygen molecules apart and reform them as a gas phase hydrogen peroxide molecule. So you can see H2O and O2 coming together as H2O2 with the byproduct of just a free oxygen that ultimately will get used up in another one of these reactions. And these machines, they come in several different forms. They're the one form, which is really what we use in a lot of situations within our hatcheries, is called a sentry. These sentry units are standalone units, so there is actually a fan built into the bottom of the machine. You can see that the photocatalytic membrane is there on the top by the screen. If you look at that picture kind of in the middle with the white box, you can see that light that activates that photocatalytic reaction internally. And so the fan will blow, it will push air, which draws in the humidity and the oxygen across that membrane. The light activates that photocatalyst on the membrane, and then the fan pushing the air actually blows the gas phase peroxide off of that membrane into the ambient space. These sentry units are very useful in places where the central heating and air system just doesn't supply enough air to the entire space, right? To treat an entire space. And in a lot of our hatcheries, if we're honest, a lot of our hatcheries aren't very new, especially in the US. They may or may not be state of the art, right? So the central heating and air may not really reach all the places that we need to try to sanitize in a hatchery. But in the case where there is air being supplied through a central HVAC system, they have blade units, which is actually what I showed in a previous slide. And you can see here on the picture on the right. And these blade units are just installed inside the register of the air handling system. So the natural air moving through the air handling system pushes that ambient humidity and oxygen across the catalyst. Same photocatalytic light, same membrane, just utilizes the natural air movement within the hatchery. And in our studies, we've utilized both of these units depending on where we needed to supply DHP. So when Synexis came to University of Georgia, came to the Poultry Diagnostic and Research Center, the PDRC, where I am, and asked, he said, hey, we want to investigate trying to do some application of DHP in the poultry industry. Where do you think, or what do you think we could do? And my first reaction, as I mentioned before, was to go into the hatchery. We've got some kind of defined targets within the hatchery. We've got the surfaces, we have the eggs. Processes are more controlled in the hatchery, right? So definitely compared to, say, a breeder farm or a broiler farm, there should be less organic material present within a hatchery. They're already doing a cleaning and disinfection protocol, right? So a lot of the microbes should be taken care of. So let's start there, but obviously before we can go to a commercial company and say, hey, can we install this technology and see if it works? we're going to need to show that at the very least, it's not going to do any damage to the product, the chicks that we're actually putting out in this hatchery. So the initial study that we ran was at the University of Georgia on our poultry science research farm. And we collected almost 2,000 eggs from a 39-week-old breeder flock. And we placed these eggs into an egg cooler that we have on farm. And we treated the eggs and the egg cooler for 7 days with DHP. Then we repeated that process with no DHP present, another 2,000 eggs from the same breeder flock, right? So trying to control those variables as much as possible. At the end of 7 days for each group, we incubated and hatched these eggs, and then we looked at several different parameters, which we'll talk about now. So one of the first things that we evaluated was, total airborne microbes in our egg cooler. And, being a research facility and being proud of our facilities, we had thought that, there probably wouldn't be a lot to see here. But prior to beginning the study and taking a baseline open air plate on blood agar, we could see that we actually have, some bacteria and fungal spores floating around in our egg cooler. Now, this was not what we wanted to see, but it's the reality of the situation for the egg cooler that we have. And this is also fairly indicative of what you're going to see in the poultry industry too, depending on what kind of hatchery, how new it is, what kind of surfaces and materials the hatchery is made of, right? But at the beginning of the trial, we put the DHP machine, the Century unit from Synexis, into our air cooler. And 24 hours later, we did another open air plate. And you can appreciate almost immediately, within 24 hours, significant reduction in both the number and the type of growth we have on our blood agar plates by 72 hours of treatment. And at 72 hours, this was with eggs being brought into the egg cooler. So we're bringing new contaminants in at this point. You can see we've almost eliminated our airborne microbes down to just a colony or two, right? And this was one of the more striking details from our environmental sampling from this study. So then we move forward and we look at the actual hatch data, and the overall hatchability and the hatch of fertile for eggs that were treated in the egg cooler with DHP, which are the red bars in this graph, was significantly higher than the eggs that were not treated with DHP in the egg cooler. Remember, these were eggs from the exact same breeder flock held in perfect environmental conditions at the research farm. So, an increase of almost 2.5% here in hatch was statistically significant. Obviously, that's biologically significant as well when we think about the poultry industry and the scale number of chicks are being hatched. But, at the very least, it was good numbers to see from our initial research study. So to summarize this trial, at least in our controlled research setting, DHP did no harm, and it actually improved hatchability, which was, a bonus that we didn't really expect when going into the initial study. It gave us confidence to now take this information and try to partner with one of our commercial hatcheries and say, hey, can we install this technology in your location and collect some data and see what happens? And if you want more information on this study, we actually published it in Poultry Science a few years ago, right? So out of this study, we took this information and we went to a commercial hatchery that's near the University of Georgia that we have a good relationship with, and said, based off of this work, would you allow us and allow Synexis to come in and install machines in your hatchery, let us turn them on and just collect a lot of information, collect a lot of data. The hatchery that we ended up partnering with was actually set up in a very interesting way to where we had two sides of this hatchery that were pretty much identical. So this side of the hatchery has an egg holding cooler here. You've got your incubator hallways and you've got your hatcher hallways here. And then all the eggs and chicks come back together here in the chick sorting space. They get stacked here and then loaded onto trucks. So we treated one side and then treated the common space in the middle and did not treat the other side with DHP. Now, the green boxes represent Century units, as you can see in this picture. The blue boxes with a number represent the blade units, which are the ones that are installed directly into the HVAC. The number is how many blades per register were installed. All right, and then one thing to note about this hatchery is this was a very old hatchery. It had been in continuous production, poultry production, for nearly 80 years. And they used formaldehyde in their bacterial control program in the hatcheries. We did not change any of their hatchery practice. All we did was install the DHP machines, add that on top of their routine cleaning and disinfection and their formaldehyde program they used during hatch, and just collected a lot of data. Now, for sake of time, and because we have several studies to go through, I'm not going to show all the data, but one of the more interesting data points that we saw was the microbial load as indicated by ROU value. So taking ATPase swabs in the processing room. So where after the chicks get sorted from the eggshells, they get counted and vaccinated. So in surfaces within that space, you can see at the beginning of the trial, we had a decent amount of microbes, and there were spikes from time to time, right? But overall, the general trend line was for this nice reduction in overall microbial load that continued to decline the longer that the technology was being used. I should have said in the beginning, this was a 26-week, so 6-month study where we collected data with an additional 3 months of baseline data collection prior to the study beginning. So again, in this study, just as we saw in our research trial at the University of Georgia, there was an increase in the hatch-a-fertile of eggs that were incubated and hatched on the treated side of the hatchery versus eggs that were incubated and hatched on the non-treated side. Now, in this case, it was not statistically significant, but a 0.6% increase in hatch-a-fertile is biologically significant, and for this hatchery, worked out to about 8,000 chicks per week, right? So you can imagine 8,000 chicks extra a week being placed on farm is going to create some economic value. One of the more striking significant differences that we saw was a reduction in fungal spores, or reduction of chicks that were positive for fungal spores in their lungs after hatch. So this hatchery incorporates a chick monitoring program where they take newly hatched chicks, they would send them up to the Georgia Poultry Lab network for microbial assessment, and doing lung impressions for mold, for fungal spores, is one of the tests they ran. So the hatchery baseline and what we see on the eggs and chicks that were incubated and hatched on the side of the hatchery that did not receive DHP treatment was about 70% of those chicks were positive for fungal spores in the lungs, whereas chicks that were hatched on the treated side were only about 55% positive, which again, that's biologically significant, but statistically significant in this instance as well. Now, again, you may think, wow, 70% of the chicks coming out of this hatchery had fungal spores in their lungs. But if you are familiar with the poultry industry in the US and the way that a lot of our hatcheries have been adopted and adapted into being hatchery spaces, and again, this hatchery has been in production for almost 80 years, and there are a lot of inefficiencies within the hatchery system that can lead to things like fungal growth. You probably aren't actually surprised about that number, but it was good to see that we had a significant reduction. So let's switch gears just a second. We've done 2 research studies now to, evaluate the ability of DHP to have an impact on, kind of overall cleanliness, hatchery performance. But the question that I would get asked a lot, and honestly was a question that I part of the trials that I'm not involved with, how much does this system cost, and what incentive do I have to install that new technology in a hatchery? I said, well, the incentive would be this new technology is going to have to pay for itself somehow. So, hey, that's where those extra chicks come in, right? So let's be conservative and say we had a 0.5% increase in hatch, which for an average size hatchery in the US would be about an extra 6,000 chicks per week. If you take industry average from AgriStats on average livability, and then you take that and you multiply that out by dock price per pound, an extra 5,700 birds going to processing would be an extra $35,000 a week at the processing plant. But if you take a step back and you look at the vertical integration within our poultry system, that $35,000 doesn't go back to the hatchery. It doesn't get attributed back to gains made at the hatchery. One of the pitfalls of our production system is that hatcheries, even as critical as they are, as that focal point within the production system of a lot of different microbes, fertility, everything, the hatcheries are thought of as cost centers. You spend money in the hatchery. You don't generally make money at the hatchery. You make money at the end of grow out, or you make money at processing. All right. So equating the value of these extra 6,000 chicks or these extra 5,700 birds going to processing, it's kind of hard to do, and kind of hard to actually bring that back to the hatchery and say, that it's a cause and effect relationship. So that's kind of what led us into the last research question here, which is, evaluating and comparing DHP to something we already use in the hatchery, like formaldehyde. Now, formaldehyde is a very potent chemical. It has bactericidal, fungicidal, virucidal, sporicidal activity, right? It basically kills anything that it comes in contact with. It cross-links proteins, and it does that very effectively, and it really is unbiased at what type of proteins it can cross-link, right? So it can work on pretty much anything. Hatcheries do develop their own formaldehyde application protocol. My wife, when she worked in a poultry hatchery, was involved in developing their formaldehyde protocol as they removed in-feed antibiotics and became antibiotic-free production. But it typically involves having some sort of container, a jug, a bag, some sort of container of that liquid formaldehyde that is then drawn into a hatcher via a wick inside the hatcher. And then once that wick is soaked with the formaldehyde, it will volatilize into the air. And once it's in the air, then it will fight the airborne microbes in the hatcher. Now you think, why in the hatcher? Why not use formaldehyde during other steps? Well, if we think about what's going on in a hatcher, that's when those chicks are hatching. They're pipping out of the eggshell. If we recall, those microbes are going to move through the eggshell that are on the surface of the egg during the incubation process. And so as those chicks begin to break out of the eggshell, all those microbes are then released back into the air. We call it a microbial bloom, right? So we're trying to fight that bloom. And this is a typical formaldehyde application protocol. We call it formaldehyde drops, right? So they are about every 6 hours for the time that the eggs are in the hatchers. And then you stop 12 hours prior to actually pulling chicks out of the hatcher. But if you're familiar with hatcheries at all, you know that most of the chicks have already hatched before 12 hours prior to pull, right? So not only are the eggs being treated, but the chicks are getting dosed with formaldehyde as well while they're in these machines. So why would we want to replace it if it's so effective, though? Well, you probably saw in that last slide on the MSDS sticker that it is a dangerous carcinogen. It's already banned in 6 states. Formaldehyde use is currently under federal review. And to be honest, it's probably only a matter of time before it's banned nationwide. And the EPA requires that employee records be kept for 30 years for any employees that have come into contact or been exposed to formaldehyde, which is a pretty large company burden. Here's the OSHA fact sheet for formaldehyde. Acute exposure is highly irritating to the eyes, nose, and throat, can make anyone cough and wheeze. You may have allergic reactions of the skin, eyes, and respiratory tract. I've actually experienced this. I've gotten a formaldehyde rash on exposed skin from going into hatcheries where they were really using a high concentration of formaldehyde. All right, so it's a harsh chemical, which is why it's effective, but it is harsh and dangerous for hatchery employees and for the chicks themselves. And because of this, for a long time, a lot of people have been doing research trying to see if there are alternatives that can be used in commercial hatcheries to try to get rid of formaldehyde, just because of its carcinogenic ability and the negative impact it can have. All right. So this felt like sort of a natural segue for our research as well. So looking at our last study, can DHP, dry hydrogen peroxide, actually replace formaldehyde in a commercial hatchery? And so again, before we went to a commercial hatchery and said, hey, let us turn off your formaldehyde program and install this DHP, we wanted to try to collect a little bit of data. So we partnered with a company over in Europe who had a smaller scale hatchery that did a formalin egg wash prior to incubation, but did a lot of microbial swabbing on eggs. And so they allowed Synexis to go in and apply DHP machines directly inside of single stage incubators. And then they compared swabs of those eggs to swabs of eggs that had been treated with formalin prior to incubation. And if you look at the gold line compared to the orange line, you can see that by embryonic day 7, so by 7 days of incubation, There were almost no microbes present on any of the eggs, DHP treated or formalin treated, and there was no difference between the two groups. So this gave us some good indication that given enough time for treatment, that the DHP could impact microbes on the surface of eggs in the same way that a formalin wash would do. So again, we took this information, we were able to partner with another hatchery that was close to University of Georgia. It was a hatchery that utilized single stage incubators, which is important for supplying that DHP directly into those machines and allowing it to build to a concentration, particularly in that early incubation phase when there's not a lot of air turnover. And the hypothesis for this study was that DHP would be just as effective as formaldehyde at controlling microbes and maintaining hatchery performance. We weren't expecting that DHP would, somehow magically outperform and do better and blow formaldehyde away, but our expectation was that it would be just as effective. And so to go through this experiment, the experimental design, we collected baseline data from this hatchery for 3 months, which was about 14.5 million chicks hatched. During this time, the DHP units were installed throughout the hatchery. We did not turn them on. They were just installed and plugged in, not turned on. Hatchery continued a normal C&D and formaldehyde procedure. We then had phase 1, which was 4 months, approximately 24 million chicks. And here is where we turned the DHP units on in the locations we were going to treat. We did this in addition to the routine cleaning and disinfection protocol and the formaldehyde procedure. So we didn't ask them to turn formaldehyde off at this point, just add DHP on top. So very similar to our first study that I showed you, our second study, our first hatchery study. Then in phase 2, another 4 months, another 24 million chicks. We then turned formaldehyde off in certain hatch halls in trial 2, or in phase 2, so that we had a direct comparison of DHP treatment to formaldehyde treatment. Now, this hatchery, this is a layout of the actual hatchery. You can see here the green boxes again represent those Sentry units. The blue circles represent blade units that were installed in the HVAC. We installed machines directly into this incubator hallway. So every individual incubator had 2 Synexis DHP units installed here. We installed Sentry units in the plenum space above these 2 hatcher hallways so that when the hatchers called for fresh air, they would draw treated air into the machines. These 2 hatcher rooms were physically separated by a concrete wall that went floor to ceiling. So there was no transfer of DHP treated air from this hatcher hallway to this hatcher hallway. And then again, we treated common spaces like the egg room and the transfer room where in novo injection was occurring. So to look at the different treatment groups that we were going to have during the study, again, during baseline, there was no treatment, no DHP treatment. This was standard routine hatchery practice. So no treatment in the egg room, which is represented in gray, no treatment in any of the incubators or incubator hallways, which are represented here in pink, no treatment in the transfer room, which is in blue, and just the standard formaldehyde treatment practice in the hatchers represented in this yellowish color here. During phase 1, we did treat the egg room with DHP. We treated that 1 hallway of incubators with DHP, but did not treat any of the other incubators. We did treat the transfer room, the transfer space where the in novo injection was occurring with DHP. And then in the 1 hatcher hallway, we treated with DHP in addition to the formaldehyde. In the other hatcher hallway, it was just formaldehyde treatment. Phase 2, nothing changed except in the hatchers. And then in 1 hatcher hallway, we did turn formaldehyde off completely and just treat DHP. And in the other hatcher hallway, again, they continued their standard formaldehyde treatment program. Now, there are kind of there was a little bit of an experiment within an experiment here within this study. And if we look at the basically egg room to incubator to transfer room, there's really no difference between a lot of the phases. You have your baseline where there's no treatment. You've got phase 1 and phase 2 where there is treatment and the treatment is the same. All right. And so we wanted to look at some parameters during that initial portion of the study, which in this case was egg swabs using, again, those ATP swabs. Now, we looked at a lot of other parameters that we're going to go through, but just for a second, I want to focus on these ATP egg swabs. Because of the way the hatchery is set up and because of how we designed the study, we had eggs that were moving through treated incubators and we had eggs that were moving through untreated incubators, so no treatment at all. That would then come back out into the transfer room. So it gave us a very interesting opportunity to directly compare the microbial load on the surfaces of these eggs in a DHP treated environment inside the single stage machines versus a non-DHP treated environment. And so if we look at those values, we can see that the average ROU value of all of these eggs coming out of the egg room before they went into any incubators was 1,356. And you can see from this graph that whether the eggs were treated, which are the red dots, or untreated after that, there was a significant reduction in surface microbes. For the treated group, there was an 86% reduction in overall microbes on the eggshell. For the untreated group, there was an 81% reduction in overall microbes. So this shows us that naturally there is a lot of eggshell surface decline in microbial load. What that doesn't tell us, though, is that decline actual microbial die-off, or is a lot of that the microbes actually moving through pores into the shell at that point? I think there's probably some of both. But if we compare the treated versus non-treated values to each other, there actually was a significant difference in average RLU value indicating microbial load on the surface of those eggs, right? And even though these numbers are not dramatically different, we do see a statistical difference here. This actually is an interesting data piece when in consideration of the next data I'm going to show you, which is the hatchery performance. So we go back to our treatment groups. We were just looking at eggs, sort of a trial within this first portion. But now let's look at all the different treatment groups that we have within the main section of this study. So we are going to have some incubators and hatchers which are going to be treated throughout the entire process, what we call our TT group, right? So during phase 1, they're getting DHP treatment in the egg room. They're getting DHP treatment in incubators. They're getting DHP treatment during transfer, and they're getting DHP and formaldehyde in the hatchers, right? And then we go to phase 2, they're still getting the full DHP treatment and just DHP in the hatcher. We are going to have some eggs that have some sort of combination where they get treated in some places, particularly in the beginning of the hatch process, and not treated with DHP later. Vice versa, we have some eggs that are not going to be treated during incubation, but will get treated with DHP. Then we have our other, what we would consider our control group, that receives no DHP treatment at all, except in the egg room. We only have one egg room, so we weren't able to separate these two spaces, but these eggs were in the egg room for at most 24 hours, so not a lot of treatment going on there. All right, so we look at all these treatment groups together. This data set was quite complicated, but for the sake of this presentation and really comparing the groups that we wanted to understand better, we are just going to look at data from eggs that were fully treated with DHP the entire time to eggs that were not treated with DHP at all, except for that small amount of time in the egg room. So the TT group versus the UU group, treated versus untreated. Again, going back to our list of parameters of interest, we looked at a lot of data from surface swabs, in-house quality assessment reports. We took 3-day mortality. We sent 3-day mortality all for necropsy. We did microbial evaluations of that necropsy. And across all of those metrics, everything that is outlined in red, there were no significant differences between either of the treatment groups, right? So whether the eggs were treated with just DHP or just with formaldehyde and no DHP, no differences. Okay, which actually fits into our hypothesis. Our hypothesis was that there would be no difference. And so we saw that with those metrics. But now let's look at these other two, fluff counts and hatchability. So you may appreciate here when looking at fluff counts, this would have been during baseline data collection. So there was no DHP treatment going on. The hatchery was just using their standard formaldehyde protocol and open air plates. So the fluff count is basically a 5-minute open air plate inside the hatcher as the chicks are hatching. And you can see that most of those values are TNTC, too numerous to count, right? A lot of microbes present. Again, highlighting the need for some sort of treatment in those hatchers. Now, when we moved into phase 1 and we look at the groups in yellow, which are getting formaldehyde only, versus the groups in green, which were receiving DHP and formaldehyde, we don't see a difference. It's still TNTC, too numerous to count. We move into phase 2. Now, the yellow groups are getting formaldehyde only. The groups in blue are getting DHP only. So we have actually turned off the formaldehyde entirely. And again, still too numerous to count, right? So you may ask yourself, why am I showing you this data? Well, numerically, quantitatively, there was not a difference between these groups. But looking at the plates, just like I showed you in our very first study in our own research egg cooler, qualitatively, you can appreciate these three plates were from the same hatcher. So these plates were taken from the same hatcher during baseline treatment when it was just the standard formaldehyde program, during phase 1 when formaldehyde and DHP were being applied, and during phase 2 when only DHP was being applied and no formaldehyde at all. And so qualitatively, you can appreciate that there are less bacteria on that plate when just DHP was being applied compared to the other two groups. This was a blood agar plate, or I'm sorry, McConkey agar plate. If we look at a tryptic soy agar plate, TSA, so targeting, different type of bacteria, we see the same trend hold true. While they're still technically, quantitatively too numerous to count, qualitatively, we can see that there is a reduction in microbes. I'm showing you these images as sort of representatives, but this held true for pretty much all of our hatchers throughout the study, which leads us into the hatch data. So if we look at hatchability by treatment group, during baseline, the eggs that were moving through those machines that were going to be treated with DHP, the just standard hatchery practice hatchability was 82.77%. During phase 1, when DHP was turned on and you were getting DHP treatment and formaldehyde treatment in the hatchers, hatch actually declined very slightly, 0.2%, but was not significantly different compared to baseline. But during phase 2, when formaldehyde was turned off and just DHP was applied in the incubators, in the transfer room, in the egg room, and in the hatchers, there was a significant increase in hatchability, over 3% increase in hatchability. Now, if we look at our control group, so this group received no DHP treatment at any point in time except for that small window in the egg holding space. These incubators started off hatching higher. That's just the natural flow of the hatchery. These machines hatched at a higher rate. So they started at 86.08%. During phase 1, there was a slight decline to 84.6%. So this shows us that just during that phase 1 time period, the hatchery itself declined in hatchability overall, right? So there are seasonal differences within hatcheries, and I think that's what we see here. This was a significant decline compared to their baseline, however. But then in phase 2, there was a slight increase again in hatchability, which was significant compared to phase 1, but was no different, almost identically numerically to the baseline hatchability. So this portion of the hatchery, these machines hatched at about 86% for the entirety of the study. So there was no increase throughout the study, whereas in the groups treated with DHP and DHP only in the hatchers, we saw that 3% increase in those machines. So you take all this data together, we saw the reduction in microbes on the eggshell. Again, while not a large reduction, there was a significant reduction there. We saw the increase in hatchability. We saw the decrease qualitatively in our open air plates, showing this decrease in microbes in our hatchers. And we put all this together, and I think from these studies, we can say that the long-term application of DHP during incubation had a significant positive impact on eggshell microbes going into the hatchers. I'd like to repeat here that, these were single stage machines, and that's one reason we targeted this particular hatchery to partner with, because it enabled us to treat inside those incubators. That's 18 days of direct concentrated treatment within those machines. And that was, I think, a key portion to the design of this study. When we look at the DHP treatment in that treated group, we saw a 3% increase in hatchability during treatment compared to machines that were not receiving DHP. So that was a significant increase from the way those machines are operating before the DHP treatment. But it was also, if we look at these values again, that was not significantly different from the formaldehyde only group, which, if you recall, hatched at a higher rate to begin with. So not only was there a 3% increase in the machines that were getting DHP, that increase brought the hatchability of eggs coming through those machines on par with other machines within the hatchery that were already hatching at a higher rate. And interestingly, both of these takeaways match data that we've seen in previous studies. I've shown you two studies that we've done, which were two of our larger studies. We've done other smaller studies where we've seen the same impact. And in evaluating data from these trials that we've done, from other instances where we've been able to collect data from hatcheries that have installed the DHP equipment, that improvement in hatchability is one of those numbers that is very consistent across all of these different research projects. So going back to our parameters of interest, we had an improvement on egg swabs. We have a qualitative, that visual improvement in microbial load and fluff counts. We definitely had an improvement in hatchability. And so to bring it all the way back around to our overall trial, DHP will be just as effective as formaldehyde at controlling microbes. In this particular study, we were able to prove our hypothesis correct. At the least, DHP was as effective as formaldehyde at controlling microbes and maintaining that hatchery performance. And actually, we saw an increase in hatchability in the hatcheries where DHP was being used. So to summarize and finish up, as I showed earlier, there's a lot of novel technology for hatchery sanitation coming out because the mindset of the hatchery being a place to really get these chicks off to a good start is changing and evolving. And there's a lot of work going into this. And so alternative strategies for controlling microbes are continually being sought after. That use of formaldehyde, we do still use it now, but it is a human health hazard. It's a chick health hazard. And as I mentioned earlier, it's under federal review right now. So I wouldn't be surprised if it's just a matter of time before it actually gets removed altogether. So any strategy that can move us away from that formaldehyde is going to be welcome within hatcheries, particularly if you can show that cost offset or that improvement or at least maintenance in production parameters. After all the work that we've done, I think that DHP is one of those technologies, one of those strategies that can be implemented to help maintain our hatchery performance, perhaps even improve our hatchery performance in this era of, antibiotic-free production, of a big focus on maintaining that hatchery sanitation and cleanliness procedure to get those chicks off to a better start, which is going to lead to a better health outcome for them, which is ultimately more birds to processing and more meat that the companies can put on the table. So with that, I'll say thank you. I believe now Synexis has another slide or two to go over with you. But I will be happy to also take any questions if there are any questions from the audience. And I believe maybe we would put those questions into the chat. So I see we have one question here in the chat. During the use of DHP, hatch increased by 3%. What was the specific improvement? Reduction on late dead, early dead, bacteria? How can you just improve 3%? That's a very good question. So we did evaluations of all those things. We did residue breakouts looking at early dead, late dead, overall bacterial contamination. In the initial study that was done in our research setting, it was a reduction that correlated. That was a 2.5% or so increase that correlated to a reduction in late dead. In the two hatchery studies that we looked at, it was sort of spread across early, middle, and late dead. Middle dead, there wasn't a whole lot of difference. Middle dead is a very low percentage anyway of the total embryonic mortality. But there was an improvement in early dead and an improvement in late dead, which accounted for that difference in overall hatchability. But that's a great question because you're right. How can you just improve 3% in hatchability, right? You can't make chicks, infertile eggs hatch or anything like that, right? So it was a combination of those two, of the early dead and the late dead improvements. So there were two other questions that were already answered in the chat. Validation for the reduction of salmonella and other hatchery pathogens. And yes, I believe Synexis has all that data on file. So we didn't do any specific reductions looking at individual types of bacteria. It was just an overall metric. But I believe Synexis does have that data. And another question, won't formaldehyde reduce the amount of DHP? Actually, yes. And that's one reason why I didn't show the groups here that only received a partial DHP treatment or sort of that additive DHP and formaldehyde in the hatcher phase, because we did take into account that, yes, the DHP and formaldehyde probably would just work to neutralize each other. And which was again why we wanted to do this in phases, though, so that we could try to see what the impact of that overall was. And it seemed like, at least from this last study, that going into the incubators in that single stage incubator system with that 18 days of treatment there where those eggs were confined was really the additive beneficial factor that helped with that improvement in the numbers that we saw.
We'll go ahead and wrap up our webinar for the day. Have a great day, everyone, and thanks for attending.